Today, we will look into how to use the right-hand rules. The different right-hand rules are mnemonic devices for remembering directions relevant to different things in physics, but especially for revolutionary motion and magnetism. In particular, when dealing with magnetism, the right-hand rule helps us figure out the direction of the Lorentz force, the direction of a field within a loop of current, and the orientation of a magnetic field due to a current-carrying wire. The first application is the Lorentz force. This is what happens when a magnetic field exerts a force on a moving charge. The formula F equals qv cross b means that a charge with magnitude q and velocity v moving within a magnetic field b will experience a force in the direction v cross b. Velocity, magnetic field, and force are all vectors in this equation. In this example, we have a magnetic field traveling into the board. We would like to send a charged particle into this field and figure out what direction it will take. Assuming we start with our particle moving in the upwards direction, we know the velocity and we know the magnetic field, so we can figure out the force that will be exerted on the particle. Using the right-hand rule, we point our finger first in the direction of the velocity. Then, we take our middle finger, point it perpendicular to our pointer finger, and put that in the direction of the board with the magnetic field. Our thumb will point outward in the direction of the force, so our charge will travel upwards because of its velocity, and then its acceleration will cause it to curve to the left in a circular path. In this example, our magnetic field is moving out of the board rather than into the board. If we set up our particle to be entering from the right side, we must now find the new force vector. So, again, we point our pointer finger in the direction of the velocity, point our middle finger out perpendicularly in the direction of the magnetic field that is coming up out of the board, and then our thumb points in the direction of the force. So, in this case, our particle will move to the left and then curve clockwise in a circular pathway. As electric current is technically nothing more than charges moving down a wire, current has a magnetic field. In this equation, B is the magnetic field, I is the current traveling in the wire, and R is the distance away from the wire. The magnetic field due to the current in the wire will circle the wire, depending on the direction of the current in the wire. In this example, we have a current-carrying wire where the current is moving to the left. We'd like to know what the orientation of the magnetic field due to the current is going to be. So, for this right-hand rule, I'll imagine that I'm grabbing the wire with my thumb pointing in the direction that the current is moving. If I were to grab the wire, my fingers would have to curl around the wire. The direction that my fingers curl shows the direction that the magnetic field will take. So, the magnetic field will travel around the wire in a loop, like so, where, with my thumb pointing in the direction of the current, my fingers curl around in the direction of the magnetic field. Here we have another wire. In this case, the wire is oriented vertically and the current is traveling in the downward direction. So once again, we'll take our thumb of our right hand and point it in the direction that the current travels. When we do so, our fingers curve around the wire as if we were to grab it, like so. Therefore, the magnetic field traveling around the wire moves something like this. With the current traveling down, and our fingers curving around like this. If we take a piece of wire, loop it, and then send a current through it, the magnetic field will be directed through the plane perpendicular to the loop. At every point along the loop, the current will be creating a magnetic field. Tightly winding multiple loops on top of each other produces an object known as a solenoid. The solenoid's magnetic field will increase in strength depending on the number of turns of wire it has. Here we have a current-carrying loop. From our perspective, the current is moving in a counterclockwise direction. Using the same right-hand rule as before with the wire, we put our thumb in the direction of the current, and at any point along the loop, we can curl our fingers to show the direction that the magnetic field is traveling in. At any point that you pick along the ring, you'll see that inside the loop, the magnetic field is traveling upwards out of the board, because our fingers curl upwards out of the board. Outside of the loop, however, the magnetic field is moving into the board, because when we curl our fingers outside of the loop, our fingers point downward. Here we've constructed a solenoid. A solenoid consists of multiple coils of wire. In this case, the current enters from the right side and begins to curve around the solenoid before exiting at the left side. Here, the current travels in a corkscrew fashion, and because of the shape orientation, our corkscrew can be traced with the curve of our fingers. If we curl our fingers in the direction that the corkscrew travels, then our thumb will point in the direction of the magnetic field inside the solenoid. This gives us the magnetic field within the solenoid.